I was asked to do a takeaway message to start with. Basically, we're saying soil water can be measured in an effective way, and I think we probably all know that. But I would argue that it's unrealistic to think you can get super accurate with this. There's too many variables going on out there to make it super accurate, particularly the soil types, the sorts of sensors we use, the way we install those sensors, and also the process we use. They all are against you in terms of getting super accurate measurement. But there are some technologies, and we'll talk about them now, that have potential for you as consultants, agronomists, to provide your growers with information of value. We all know that soil water is a major driver of crop production. No one's going to argue with that, I don't think. But it's commonly measured or estimated using your own experience, your intuitive knowledge. You've been around long enough to have a fair feel for what's going on, or supported by push probing or coring, touching and feeling, taking a core, touching and feeling, that sort of thing. There's an increased use of real-time monitoring, and certainly there's a push in certain areas of Australia for real-time monitoring. If you go to the south of Australia and also to the west, there is a real push on particular technologies down there. And I must say right from the start, this presentation is about cracking clays, the soils of the north. It's not about all soils, and it's not about irrigation particularly, it's about dryland agriculture. And that has implications on the sorts of things that I will be talking about. Technologies that I'm talking about for dryland systems on cracking clays are effective in other parts of Australia but aren't on the soils we're talking about. So the two questions I want to ask here are which tools are adequate to measure or adequately able to measure soil water across the range of soil water that we're talking about from wet to dry, and that's not always the case with all technologies. Which ones are commercially applicable and which ones can work on the cracking clays? How accurate are they? And are we having a lend of ourselves when we try to go for super accuracy anyway? This was done at Norwin, this work on the Downs. It was a black vertisol, a mobile soil for those that know the soils of the Downs. High plant available water capacity, drained up a limit of around 50%. And PAWCs of between 250 and 300 for wheat and cotton. Pretty typical of the northern cropping soils in terms of productivity and PAWC. The experiment we did there was a replicated experiment over an area of about 400 square metres, so quite a small area. Three crops in sequence over 2 years, and we logged continuously through that period where we were logging, and we did point scale measurements every few weeks over that period for the appropriate technologies where we did need to do that. Okay, the technologies we use, capacitance probes or FDRs, which quite a few of you will be familiar with. There's certainly some of those being used around the place. With calibration, you can measure volumetric water with those. You can get that as an output. We also looked at some of the very old technologies that have been around and used quite a bit in tree crops and viticulture, that sort of thing. The gypsum blocks, which measure matrix potential, again layered down the profile depending on how many sensors you have in the ground. And the third one of the in-situ devices, so this is real-time monitoring in-situ devices, was the TDR, the time domain reflectometry, which again provides, with calibration, an estimate of volumetric water content. The difference between this technology and this technology in terms of installation, and that's an important difference I feel, this one's put in from the surface, and this one's put in, or can be put in from the side, so in a pit, which makes it more difficult to put in, but has some advantages. We also wanted to get some comparison with technologies that have been around since Adam was a small boy, including neutron moisture meters, which again with calibration gives you volumetric readings. This is a mobile device, but it's still at the point scale, and as we all know, you need an access tube for those. And the other one we wanted to look at in terms of the in-situ devices was the use of electromagnetic induction, which is a measurement of bulk soil electrical conductivity, and it provides an overall estimate of water to depth of measurement. So that means you don't get layers as you do with most of the other devices, you get a bulk measurement of available water, or of water content. I'm going to talk a little bit more about this because this is one we think there is potential for in the future. I just wanted to give you a little bit of an idea of how it measures. When I say that it measures the overall estimate of water, the device has dipoles, either the vertical or the horizontal dipole. When you use those two in combination, it allows you to measure to a depth of about 1.5 metres with the, I never remember which one it is, horizontal, isn't it? Yeah, the horizontal one being more effective in the surface, and the vertical one being less effective at the surface but reasonably effective at depth. So between those two measurements, you get an estimate of water over that depth. Neal Huth, who's my co-author, is the guy that's done most of the work on the EM, so any questions later we'll flick to Neal. The other technologies we wanted to talk about were simulation. Modelling of water balance and crop production's been around for quite a few years now, and the ones I'm talking about, APSIM and yield profit. We wanted to use that as a way of predicting soil water, and so that's one of the comparisons. And we had to have the good old control, gravimetric as a control, something that we're all familiar with, taking holes in the soil and doing gravimetrics, and we decided to use that as our control. So what did we get out of this? This is in the top 15 centimetres of the soil profile, and this is comparing TDR, the capacitance probes, so the enviroscans, with gravimetrics, the red ones, and with neutron moisture meters, which are probably a bit hard to see for most of you down there. What this is showing is that all of the technologies tend to track rainfall reasonably well. So dry period in there was a wheat crop being grown in there, soil moisture's dropping from up around 50% volumetric down to about 30% volumetric. So getting close to crop lower limit, probably not quite there, but fairly close. So all of the technologies are doing a reasonable job, but you will see, particularly in this top layer, the 15 centimetre layer, where you've got a lot of evaporation going on, you've got a lot of cracking going on, etc., you do see variation between the technologies. One of the issues, particularly with, remember I said before, the installing devices from the surface as opposed to the side, one of the issues with the vertical or the surface push is that you tend to get cracks forming around these devices. They're basically created by the device themselves. As soon as you put something in the ground, you tend to start getting cracks around it, and you see this with NMM tubes as well. What's happening here is you're getting drying or bad or poor measurement, poor estimation of water by that device because of those cracks. But in general, not too bad. Again, here in the 15 to 30 centimetre layer, similar things, but again, some variability depending on cracking, and also potentially, as you see in here, potentially the capacitance probe there has been affected by this rainfall here, and you've had preferential flow of water down beside that device. The TDR, the black one in comparison, seems to be doing a better job of measuring soil water in a realistic way. Because there's no unnatural cracks from the surface because of the device, the water is moving down and hitting those devices in a more natural way. So in my view, we're getting a more natural and more realistic view of water from the TDR. Neutron moisture meters, again, reasonable. And gravimetrics, a bit of noise around them, and you'll see some variability around those as well. You've got to remember how we measure things with these different devices. Gravimetrics, it's really hard to get a gravimetric sample in the middle of a crack, or to get it in a ped next to a crack. It's damn hard to do. So you always go to the middle of the crack, middle of the ped. That means you're biasing your moisture contents to the middle of that ped, which may not be the reality, the average reality for the whole of the soil you're looking at. So it's quite often that you might bias your water up in that particular instance. So just keep that in mind when you're looking at this data. 30 to 60 layer, again, you'll see the capacitance probe here topping out at about 50% volumetric. And that's an issue with both the capacitance and the TDR devices. They can only measure to about 50%. So if you have soils above that have a drained upper limit above 50%, as we do, you won't get that fine detail at those upper limits of moisture. Now, I guess my view is that's probably not all that important anyway. It's just something to remember. What we're seeing here, again, is potentially this cracking issue. where the capacitance has cracked quite deep, and they did in this particular experiment. And again, you're getting air drying, and you're potentially getting poor measurement around the actual tube. And this is the last one. If we just look at these two things here, this is at 60 to 90. You can see that the capacitance device has topped out at 50, which means that there's been preferential flow of water down to that depth, and it's topping out at 50 compared to the TDR, which is probably giving a more realistic assessment. And this one here again, where there's been very little extraction of the water there, but there's been preferential flow again to some degree. There's noise around the gravimetrics, and as I said, I gave you some of the reason for that before, and I'll talk a little bit more about variability in a minute, which contributes to that as well. So those are the TDRs, the capacitance, and the NMMs. What do I say about that? I guess my view is TDR looks to be doing a reasonable job, capacitance will do a reasonable job, but if you're in a cracking soil, it's not going to work as well as TDR, we don't think. And NMM is reasonable, but again suffers from the cracking if you're using them in a dry land system. Irrigation, fine, where they're not going to get too dry. If we look at the model, I was saying we're going to use APSIM or yield profit and see what we could predict in terms of soil water. The black line there is the modelled water, predicted water on daily time step. This is total water in the profile. You can see that the model is telling us that our profile was pretty full around the start of the end of November, end of 2010, early 2011. We all know what was happening about that stage. In fact, it was flooded, and we're up at probably that'll be field capacity around there, or even a fraction more. The gravimetrics in this case are the blue triangles, and we're predicting, we're doing a reasonable job of running through there, a bit high in certain places. That's all associated with soil variability, which I'll talk about in a sec. And the EM38s are predicting reasonably well, measuring reasonably well. A couple of high ones there. Again, there's variability in the soil we'll talk about in a minute. So overall, most of the devices are doing what appears to be a reasonable job, but there are issues with certain ones of those. Let's just think a bit about accuracy. And I said before that I thought we were probably having our land of ourselves if we thought we could get too accurate. And I say there is a perception that you can do that, but think about what we're dealing with here. We've got soils that are spatially variable, both horizontally and vertically. They vary a lot, even when you think you've got a homogeneous soil. The sampling levels of intensity are low. We did a reasonably intense level of sampling in this particular experiment. It was a small area, and yet we still had problems. So imagine when you as a commercial consultant go out there where you can't afford to be out there for 2 days sampling a paddock, these sorts of, and you do what is practical from a cost and time perspective, how much variation you're going to be bringing into that. That's not a criticism, it's what you guys have to do. So how do you get around that? Or do you get around that? The technologies are open to the vagaries of installation and use, and I'll talk about that in a second. And if you're going to relate this back to soil characterisation, so plant available water, millimetres of available water, it means those PAWC measurements have been done at a point in a paddock somewhere. It might be the same soil type as you're on, but it's not going to be the same place you're in. So that's another area of variability. So at the end of the day, how accurate do we really need to be in this, and can we be in this? It comes back to me, for me I guess, is what sort of levels of information do you need as consultants to actually make decisions? Do you need to know if you're plus or minus 5 millimetres of available water to make a decision? Or are you working on some scale of 25, plus or minus 25, or even plus or minus 50? That's the question, I think. So my earlier comment, are we getting a bit too carried away with accuracy? I suspect my view is we are. And I don't think we can be much more accurate than what we are at the moment. You don't make decisions on planting on 5 millimetres, I wouldn't think. You probably make it on whether you've got 100 or you've got 10 or whatever, depending on the crop type. So what I'm saying is maybe we are trying to get too carried away here. And one of the reasons I say that, and it's come out of this experiment, we used gravimetric moisture as our standard measure of moisture content. We were taking routinely 12 cores, so 4 reps of 3 cores, and each of those 3 cores was 30 centimetres apart. And yet we were still only, within, where is it? It doesn't say there. Where the variability around the true mean was plus or minus 15 millimetres of available water to 90 centimetres. So there's a lot of variability there, even when you think you're in a homogeneous soil and you think you're sampling at a fairly high level of efficiency or replication. No one in commercial agriculture would ever do that level of intensity. You can't afford to. And it's even, in terms of gravimetrics, and it's even probably rarer, or very much rarer, to actually put in situ devices where you're spending a lot of money to put those devices in at that level of intensity. So you're going to be lower than this level of intensity, I would expect. So what causes this accuracy issue? I've talked about some of them. Soil cracking with neutron moisture meter tubes, capacitance probes, the gypsum blocks as well. And I've said that TDR, I don't think, is just as prone to that. Yes, you're going to get cracks, but they're going to be more related to the crop you've got on the top than the device you've got in the ground. Capacitance probes, so this is the EnviroScan type of probe. Some work done by Warren Bond out of CSIRO and other people on these devices showed that 50% of the signal, the measurement signal, comes from within 4 millimetres of outside the tube. And 80% comes from 12 millimetres from outside the tube. So if you've got something like this, you can see that you're going to have an issue in terms of measurement accuracy. And that's where cracking becomes a major issue when you're using these devices in shrink swell soils. In non-shrink swell soils, i.e. in the south, these things work quite well. And they're being used by a lot of farmers, a lot of consultants. But in the cracking clays, probably not all that good. Whereas with neutron moisture meters, you've got quite a large, if you're looking down the profile, 15 to 25 centimetre radius, depending on how much water's in the profile. So that's your measurement zone, quite large. So a few cracks, you can probably get away with that to a degree, but you can appreciate the measurements aren't going to be just as accurate. The EM38, this is very much a stylised view of it, but you're taking a measurement down to 1.5 metres, and it's quite a large area of soil that you're working on. Simulation is really, the accuracy is related to your bucket size, so the PRWC of the soil you're using, how good is that, how accurate is it in relation to the soil you're on, how good your met data is, and what starting conditions you've put into the system. Gravimetrics as accurate as you want to make it. It depends on how much time you can invest in sampling. So what are the pros and cons of these devices? Capacitance, it measures volumetric water after calibration, goes up to 50% volumetric, it's instantaneous, and you get layered information. It is temperature sensitive, so you have to calibrate for that or take that into account. They're fairly expensive, particularly if you want to do a lot of them. You need to be reasonably good at putting them into the ground to make sure you don't get those voids and those sorts of issues. And I think the major one here is influence of soil cracking and soil movement over time. The gypsum blocks are quite cheap, but they do break down over time. 2 or 3 years they'll break down, so you have to redo them. They're also very slow in response, so it's not an instantaneous thing. It takes quite a while for them to respond to moisture, and cracking's an issue. They're not one that I would be recommending, and also they don't measure the whole range of soil water from lower limit to upper limit. They are not very useful at the lower levels of soil moisture, and that's the area you probably want to know things in dryland systems. TDR, similar sorts of issues. Pros, instantaneous, layered soil information, similar range of measurement and point scale. Reasonably high capital expenditure. These aren't all that expensive, but then you need a logger to go with them, etc., etc. And installation's a bit more of a pain. They are influenced by EC, so electrical conductivity, that can affect the measurements, and potentially they will be affected by cracking and soil movement, but I don't think as much as the others. APSIM, you're predicting plant available water on local soil with local met data. It's a daily time step. It's layered or can be layered soil information. It's non-destructive. You don't have to go into the field to do this. You do need to starting soil moisture, but you can probably estimate that. And it gives you prediction right through the year if that's what you want. But the downsides are you need good soil information, and you need training to use these things. Although I'm suggesting APSIM and yield profit here, but the model that Dave was showing before, it's in the same sort of camp as this. And Dave's using, instead of that very detailed soil characterisation, he's divided Australia into 12 soils. So that's another way of doing it. And may well be quite appropriate because of what we're saying, the inaccuracies in the system anyway. If that gives you a reasonable estimate of what's going on, that's possibly all you need. And then we all know the pros and cons of gravimetrics. NMMs, again, high capital expenditure. They do a good job. They're portable. Radiation safety is an issue these days, and they're also not as cheap as they used to be. Require a calibration if you're going to go to volumetric, and again, accuracy is influenced by cracking and movement. The EM38, which is this device here, it's point scale, it's portable, so there's nothing left in the field, and because it's very quick, it's a matter of putting it on the ground, probably takes 5 seconds of measurement. You could increase your replication to quite large numbers if you want to, if you really do want to get a reasonable accuracy level. It's a non-destructive sampling, it's a large zone of measurement, but it doesn't give you at this stage that layering that we were talking about with the other technologies, although there are methodologies around that do that. I guess we'd say we're still testing those to see which is the best way to go. Low operating costs, but fairly high capital expenditure, about $20,000 to buy the machines that we're using at the moment. Salinity can be a problem, you need to watch that, but the last group asked the question about that, and as long as your salinity doesn't vary, as long as it's constant, it's not a major issue, but it's where it varies over time that you have more of a problem. It requires calibration, that's probably enough. Now, this is work that came out of just talking about this NMM-EM comparison, because I think somewhere there I say it's, yeah, similar accuracy to NMM. This was work done by Neil Huth and Graham Bolton, who I see in the audience here, last year, where they compared EM with NMM and the levels of accuracy, or the comparison of accuracy between those. And on the 3 sites that were done, the levels were, R-squareds were over 0.9 for all of those. So it's quite good. Now remember, this was actually done in an irrigated system where there was no cracking issues with NMM, maybe with the exception of that point there, but overall pretty good accuracy. So what I'm suggesting there is it may be a device that people look to as consultants into the future, where they're trying to get out of NMMs for the issues that we've talked about with radiation safety and expanse. This may be another option. This was just using the EM as well in Neal Huth's PhD, looking at water use from a tree line out into the crop, and I'm not going to go into detail here, but it's just basically tracking water over time at the various distances out and based on rainfall. And it did a really useful job of that. So it's a technology that's not commercially used yet, but we've been using it for a while in experimentation, and also limited with consultants. So what am I suggesting here in terms of technologies that might be useful? My view is that if you have the potential to simulate soil water, you're probably not going to do much better than that. Now, someone brought up the question in the other group, yeah, what about weeds, what about disease? And yes, that's true. The models do not take into account those things. So if you have those problems, your soil water estimates may well be out. But as long as you have plant available water information, for the plant available water capacity information, you can use things like yield profit or the product that the Dave was talking about before, Climate, to do a reasonable job of simulation of water. If you don't have that, or you want to go to a field-based technology, you need to think about the levels of information you require. I'd be suggesting that soil water is monitored on a zonal basis, so it's on a soil type. Don't try to do it over different soil types and bulk them together. The question was raised about how you do that in the other group. I'd be suggesting, if you're going to do that, look at point scale, so always go back to points and use that you know are reasonably descriptive of large areas on that particular soil type. Always go back and you build up a history over time of what's going on. I'd be suggesting that if you need to think about the number of sites you're going to be wanting to monitor with devices, and if you're a consultant running around a couple of 100 kilometres radius of wherever you live, to have something like a mobile device that allows you to quickly get around there would make a lot of sense compared to in-situ devices. You need to think about the technical expertise that's needed to run these things, install these things, maintain these the types of devices, the field-based devices. And there's also logistical issues associated with field locations devices like NMMs, like capacitance, like TDRs. Very easy to run over with various bits of large machinery. So the suggestion is to replicate as much as you can as technically and financially, that is technically and financially feasible, be that in using EM38 or any of the field-based technologies. And I'd be thinking about using technologies that have those larger zones of influence to actually to measure soil water. So trying to avoid ones, particularly where you're getting cracking is a problem, try to avoid the ones that are very small zonal areas of measurement. So TDR looks reasonable. Capacitance and NMM, certainly in irrigation, but I would be probably avoiding them in dryland systems. And we've talked about EM38. So just to finish off, having said all that about all the technologies, the bottom line is that with the variability in our fields and the vagaries of the technologies we're trying to use, you're probably dreaming if you think you're going to get high levels of accuracy. So it's a tool to give you a good indication of what's going on, but it's not going to give you down to the fine level. There's just too much variation in the system. Thanks.